Okay. So our first keynote speaker is going to be Professor Amrita Roy Chowdhury. I'm really excited to see this talk myself. So Amrita is an assistant professor at the University of Michigan. She was recognized as a rising star in EECS in 2020 and in 2021. And she was a Facebook fellowship finalist in 2021. She's also been selected as a University of Chicago Rising Star in data science in 2021. She's going to tell us about robustness against poisoning under local differential privacy. So please welcome Amrita.
Thank you, Joe, for the introduction. Hello, everyone. I'm very happy and excited to be here today. And in this talk, we will look into poisoning attacks under local differential privacy and how to provide robustness against them. Okay. Wait, my clicker isn't working. Does it work? Okay, yes. The second technical problem. Sorry about that. Okay. So I believe we are all familiar with this decentralized data analytics setting. Let's say we have a social media company Z. Every mobile phone with the Z app is a data owner or client, and we have a server owned by the company. The server wants to do some analysis on the joint data set of all the clients. But the problem here is the server is untrusted. So it cannot just collect all the data in the clear and then do the analysis. But I don't think I need to introduce the solution of this problem to this audience. We all know the answer: local differential privacy. Great. But on the flip side, the clients can also be malicious. The distributed nature of our setting makes it vulnerable to poisoning attacks. It is extremely easy for an adversary to inject a bunch of fake clients who submit poisoned or malformed data, and this adversely affects the server's analysis. So I did a quick search on Google Scholar today morning on poisoning attacks, and it returned over 2.5 million articles. So clearly, poisoning is not a new problem at all. It has been extensively researched within the broader data analytics community. With this in mind, I think the time is right for us to look into poisoning under the constraints of privacy. Specifically, a key question for us is, can we provide provable robustness guarantees against data poisoning attacks under local differential privacy? Now, to answer this question, let's first understand how can an adversary carry out poisoning attacks in LDP. So in LDP, we have a private input and a randomizer. The private input is fed into the randomizer, which then spits out the final output or response. Now, the first place an adversary can interfere with is by tampering with the input. But note that this is always possible. An adversary can tamper the input even under no privacy. But under LDP, the adversary has a second opportunity of tampering. It can tamper with the randomizer. So what this means is there's a clear separation between the private input and the privatized response in LDP. This allows the adversary distinct opportunities of tampering with the data. In this talk, we will be showing strategies to mitigate both of these types of tampering. Let's start with input tampering. So how do we protect against input tampering? Here's an idea. What if we had input redundancy? By input redundancy, I mean, what if we had another extra copy of the private input? Then potentially we could collect both the copies and check for consistency between them. In case they are inconsistent, then we would know that one of them is lying. Okay, so the problem setting that we're working with is the server wants to collect some private data of the client, and we have another entity, which I would be referring to as a copier, who has an extra copy of this private input. Now, the question is, are there real-world settings which have naturally redundant input? A very prominent example of this is graphs. Consider the setting of distributed graphs. Every client only knows its immediate neighbors, that it has access to the adjacency list. Now, every edge is shared between two clients. That is, there is two copies of every bit. Now let's look at a concrete problem setting here, a concrete problem statement here. We have n clients, each with access to the adjacency list, and the server wants to compute the degree vector. That is, it wants to estimate the degree of every single client. And the privacy guarantee that we're going to work with is LDP. Now, the threat model here is M of these clients are malicious, and they're allowed to collude together and submit any arbitrary response. So the optimal solution without privacy for this problem is Laplace. But under poisoning, a malicious client can flagrantly lie and tamper their output by up to n, the worst case possible tampering. So how do we protect against this? Let's think of the solution roadmap here. The first thing that we need to do is to be able to formally quantify robustness. Now, there's a caveat here. There's a fundamental difference between just detection versus detection and removal of malicious clients. With just detection, the only thing that the server can do is abort the current estimate. And this leaves it vulnerable to denial of service attacks. However, with detection and removal, the server can use the estimates, the degree estimates of the clients, which it believes has not been tampered with. Now, once we have a good understanding of the formal framework to quantify robustness, our first algorithmic goal should be to improve resilience against malicious clients. Now, as I've alluded to, the idea here would be to somehow leverage the input redundancy. But the problem here is we cannot directly access these inputs because these are private. The final goal is we have to protect the responses of the honest client. That is, we need to ensure that the honest client's responses still have high accuracy. So how do we go about achieving this? For this, our first key idea is that we design a framework for capturing robustness that explicitly takes into account that we can detect and remove the malicious clients. So specifically, the server here can do two things. It can either return a noisy degree estimate, or in case it suspects a client to be malicious, it can flag them and return bot. And our robustness framework measures two properties of a degree estimation protocol: soundness for malicious clients and correctness for honest clients. Okay. So the soundness quantifies the robustness of the protocol against malicious clients, and this is what it looks like. Let's parse this. A protocol is alpha delta sound if for all malicious clients, the maximum amount of tampering that they can do is bounded by alpha, or else, there is a little bit of a lag with my clicker. Okay, anyway, or else they will get flagged with very high probability, probability 1 minus delta. So what soundness means is that it restricts the malicious clients from tampering with their data by too much. If they try to tamper with the data by too much, they will get flagged with very high probability. Now let's look at correctness for honest clients. Our protocol is alpha delta correct if for all honest clients, the maximum error is bounded by alpha, and with very high probability, they will not be flagged mistakenly. So good correctness means that we can ensure accurate estimates for honest clients, even under poison. And for both the cases, lower the value of alpha, better is the robustness guarantee. Okay, so one roadblock done. Now, in order to improve resilience against malicious clients, that is improve soundness, our idea is to do the consistency check on the probabilistic outputs. So what we do is we collect both copies of the edge, noised under randomized response, and then we count the number of inconsistent bits. We flag a malicious client if this count exceeds a threshold. And this threshold is computed to ensure two things. It ensures that a malicious client will be flagged with very high probability if it tries to tamper by too much. And it also guarantees that we will not be flagging an honest user, an honest client, mistakenly. So using our formal robustness framework, we can show that the proposed protocol improves soundness guarantee. Specifically, to give you an intuition of these terms, the M term, this is an inevitable error. It occurs because of the worst case scenario where all the malicious clients are colluding together and consistently lying about their shared age. The factor of 1 by epsilon, this comes just from debiasing the noisy estimate. And the last term is the standard inherent error. Now, this guarantee here, this actually matches prior result, which studied poisoning attack for randomized response for aggregate queries. Now, one thing to note here is privacy makes our protocols more vulnerable to poisoning attacks. Lower is the privacy parameter, stronger are these attacks. Okay. Now let's see. Okay, so we have gotten around the problem of not having private access to the private inputs, but our correctness guarantee is still far from the ideal. So here our idea is to propose a hybrid protocol that combines these two approaches. So what I mean by this is now we collect two responses. In addition to the adjacency list, which is collected under randomized response, we also collect the noisy degree estimate under Laplace. And then we perform a second consistency check to verify the consistency between these two estimates. And with this, we are able to achieve the best of both worlds and recover the correctness guarantees of Laplace mechanism. Okay, so now our road is all clear and we are good to go. Now, in terms of the evaluation highlights, we evaluated 16 different attacks, capturing several real-world scenarios. And one of the observations from our evaluation was these attacks can be quite severe, even with a very small number of malicious clients. For example, the graph shown here corresponds to a graph derived from the Facebook dataset. And we have only 1% malicious clients, yet the naive protocol is 16 times worse than the hybrid protocol. Nevertheless, the protocols that I discussed are able to effectively thwart these attacks, even with a very large number of malicious clients. For example, the diagram shown here corresponds to the same dataset, but with 33% malicious clients. Here, the adversary is trying to carry out a degree inflation attack, that it is trying to inflate the degree of a malicious client. If a dot is inside the box, it means that the adversary is not successful in carrying out an attack, and it is not able to inflate the degree of a malicious client to be in the top 95 percentile. And we can see that the adversary is successful in carrying out the attack in the naive case, but it is prevented by both of our protocols. Okay, so the key takeaway from the first half of the talk is that one very good strategy of preventing input tampering is to leverage natural redundancy in the data. And we saw a specific example of that in graphs. Now let's switch gears and look into the case of tampering with randomizers. So how do we prevent that? What if there was a way to guarantee that the randomness that we're generating is honest? We would be able to solve this problem if we could somehow enforce the correctness of the randomizer. This is allowed by cryptography. So the problem setting now looks like this. As before, we have a copier who has access to an extra copy of the input. But now, in addition to that, we cryptographically enforce the correctness of the randomizer. And for this problem, we will be looking into another real-world setting with natural redundant input, the ad exchange. So here, our server is a browser called Boston, and it is a supremely trustworthy browser. So it has very high incentives to protect against these poisoning attacks. And we have an advertiser selling LLMs. But beware, these are LLMs with tails and not transformers. Okay, so the browser hosts ads on its website. And a key measurement of interest in this setting is something called the conversion rate. The event of a client clicking on an ad that getting converted to a purchase is known as conversion, and this is represented by a bit. If a purchase happens, the bit is set to 1, the bit is 0 otherwise. Now, both the advertiser and the client has access to this conversion bit. So in our case, the advertiser is the copier, and the server wants to collect this conversion bit from the client. So in terms of a concrete problem segment, we have n clients with binary bits, and the server wants to aggregate them under LDP. Now, for our threat model, again, we assume that m of these clients can be malicious, and they're allowed to collude together. In addition, now the server and the copier is also allowed to collude. Now you may ask, if the server and the copier is colluding, then why does the server need to interact with the client? Why can't the server directly just get the bits from the copier? This is prevented in our setting because of 2 reasons. First, the client's interactions with the copier and the server is unlinkable. And what I mean by this is the communication of the client with the copier and the communication with the server. These 2 communications cannot be linked together and traced back to a single client. So this means if the server collects the bit from the copier, it has no way of knowing which user's bit does this correspond to. And the way this linking happens in practice is via third-party cookies. But we are working in a setting where we don't have these third-party cookies. Browsers like Safari, Brave, they already by default block third-party cookies, and even Google Chrome's Edge, they have plans of phasing out third-party cookies. Okay. The second reason is that in addition to the conversion bit, the client sends some extra message to the server. This message is essentially metadata about the ad, which is accessible only to the client. The server needs access to both the client's identity and this extra metadata, along with the conversion bits to be able to distribute personalized ads. Now, the server collects these bits under randomized response. Without any defense, the error that these poisoning attacks introduce is given by this term. As you can see, this term is exactly what we had for our soundness guarantee in the previous protocol. And all the terms have the exact same meaning. Now let's think of a solution in a step-by-step manner. Our solution has 3 phases. The first phase is the consistency check phase, where the copier checks for the consistency of the input. Now, unlike the previous case, the check can now happen directly on the inputs via cryptography. Once the check is done, if the check passes, the copier sends an authenticated token to the client. The client then uses this token to generate a sample of biased coin and uses this to flip its private input. Now, the last stage is the verification stage, where we have to verify the correctness of all of the client's computation. To this end, the client uses the same token to generate a cryptographic proof and sends this over to the server who validates the proof. But unfortunately, we are in for a bit of a bumpy ride here. The first challenge is that the consistency check of this protocol also needs to maintain the unlinkability property that I just talked about. Which means in our setting that these 2 communications should not be able to be linked together by the content of the messages of the protocol. Now let's look at sampling the bias bit. There is existing prior work showing how to do this, but the problem is they all require interaction. And interactions are highly impractical in a lot of real-world settings, including ours. Finally, the verification of the computation of the protocols, this is done by a cryptographic primitive called zero-knowledge proofs. But zero-knowledge proofs are notoriously computationally expensive. So the challenge here is to be able to come up with an efficient construction. Okay, now let's see how we achieve this. First, for the consistency check, we provide a novel cryptographic primitive. Now, before discussing that, I want to give a little background on this cryptographic primitive called zero-knowledge proofs. So zero knowledge proof is an interaction between two parties, a prover and a verifier. The prover holds a private input X, and it wants to prove the correctness of a computation on this private input. And this computation is expressed as a circuit. For this, the prover sends a proof pi and the output Y to the verifier, who decides on the validity of the computation by analyzing the proof. At the end of the protocol, the verifier is convinced of the proof only if Y was indeed the correct output. Additionally, it learns nothing else about the private input. Okay, so back to our consistency check. First, the client needs to prepare a special message. It encrypts its private bit and then hides it with an additional random mask. Next, it generates a zero knowledge proof proving the correctness of this computation and sends all of this to the copier. The copier first verifies the zero knowledge proof with its copy of the private input X. This is precisely the consistency check on the input. If this check passes, the copier issues an authenticated token on this message. Now, this token guarantees authenticity. What this means is that it shows that it originated from the copier. Next, the client unmasks this token to generate a new one only on the encrypted bit. Now, this derivation process needs to satisfy three properties. First, the new token also needs to guarantee authenticity. Second, this given any R, given the random mask R, this derivation should be a deterministic mapping. That is, the client should be able to unmask the token only in a fixed way, in a single way. Now, this mapping is hidden from the copier because of the random mask R. And this is why we get unlinkability. The copier has no idea how this new token looks like because of this random mask. Now, the other two properties that I mentioned, why they're important, that will get clear a little bit later into the talk. But I also want you to take note of the fact that we generate this token on the encrypted bit instead of just on the bit directly. The reason for this will also become clear a little later. Okay. We propose a novel cryptographic primitive to instantiate the steps 2 and 3. Specifically, this falls under the class of cryptographic primitives called blind signatures, and we provide a new construction for it. So with this, we see how we can achieve unlinkability while still doing consistency check on the inputs. Okay. Now, for securely sampling from a biased distribution, our idea is to make the client sample locally with the help of a well-formed key. So how do we do it? First, let's assume that the clients have a magic box that can generate a sequence of uniform random bits. Now, once we have this, generating a biased coin is very easy. We just need to compare the sequence of uniform random bits with the binary expansion of the bias, and the result of the comparison gives us our biased bit. But luckily, we don't need Houdini to do this magic. The magic of cryptography suffices. Specifically, a primitive called pseudo-random function. Pseudo-random function is a keyed function. If its output is a binary domain, then we have this guarantee that the sequence of function outputs is indistinguishable from a sequence of truly uniformly random bits for a computationally bounded adversary. And the clients can evaluate this function locally. Now, for this to be working correctly, we need the key to be well-formed. Now, I mean two things by this. First, the key has to be kept secret from the server. We need these to make sure that the noise required for the privacy, for satisfying LDP, that remains private from the server. The second property is that the clients cannot generate the key completely on their own. Because if they could do that, they could cheat and select this key maliciously, and this would violate the random sampling. So what we do is, we split the key into two parts. The first component is a secret that is known only to the client. The second component, which is public, for this, we use the token that the client had generated in the last phase. Now, this is where the property of deterministic mapping comes into play. This property ensures that the client cannot interfere with the process of the generation of the token, and therefore it cannot cheat. Okay. So with this, clearly, the clients cannot generate a biased sample non-interactively. Now, for verifying the correctness of the protocol, we provide carefully optimized implementation to improve the efficiency. We have to verify three things here. First, we have to verify the evaluation of the pseudorandom function. For this, we use a specific type of pseudorandom function that is zero-knowledge proof friendly. The evaluation of this pseudorandom function essentially just constitutes computing a Legendre symbol, and verifying this is very efficient. We can do that with a very low-depth circuit. Now, the second thing that we need to verify is that we flipped our private bit correctly. This verification corresponds to evaluating the correctness of the randomized response protocol given a fixed set of random bits. Now, we saw that the general way of generating this bias bit involves a comparison operator, but typically comparison operators are expensive on a zero-knowledge proof. So what we do here is we only consider biases that are exponents of half. And as a result of that, our bias sample is simply just product of the uniform random bits that we get, which are basically the evaluation of the PRF, the pseudorandom function. And with this, we completely avoid the expensive comparison operator. And then flipping our private input can be expressed by this very simple equation. Okay. Now, the last piece of the puzzle is we have to show that we use the correct input. That is, we used an input that passed the consistency check from the copier. Now recall that the token that the client generated was also authenticated. So if we could use this token to generate the proof, then this would precisely satisfy our requirements. And we do this by using a specific type of zero-knowledge proof that is compatible with these tokens. Also, another thing that we can see now is why we require this token to be generated over the encrypted bit. Because as I just discussed, we need to send this token as part of the proof to the server, and this encryption keeps our input X private from the server. Okay, so with this, we are done with all of our challenges. Now, coming to the robustness guarantee, the proposed protocol can completely prevent poisoning attacks. Specifically, we can see now the only error that we have is the inherent error of randomized response. A note here about the privacy guarantee is we now have to work with computationally bounded adversaries here because we are working with cryptographic primitives. Now, let's look into some evaluation highlights. A caveat here, this is an ongoing work, so these are just preliminary results. What I want you to take away from this is the order of magnitude of the performance and not the concrete numbers. For instance, the communication cost for both the client and server is just a couple of milliseconds, very low. Similarly, the communication cost is also very low. It's less than 1 kilobyte. So in summary, the key takeaway from the second half of this talk is that cryptographic primitives, when carefully designed, can be very effective in preventing tampering with the randomizer. And we saw a specific example of that in the ad exchange. Now, in case you eat, breathe, and sleep differential privacy, I want to leave you with a few food for your dreams. Okay. So one of the things that I wanted to highlight here, that the privacy protocol that we were working with, randomized response, is as simple a protocol can get. Yet, robustness required highly non-trivial solutions. So here, we are literally just scratching the surface of problems here. Broadly speaking, there are two directions of research here. The first is understanding the impact of poisoning under privacy. Now, most of the work has focused on non-interactive settings. An immediate question is, what happens when we introduce interactivity in the mix? Specifically, a question can be, in whose favor does the balance get tilted now? With interactivity, can the clients make more potent attacks, or does it become easier for the server to catch a cheater? Another question is, what are the different type of adversarial effects that we can introduce? So in the talk, the adversary's goal was just to increase the overall error of the server's analysis. But we know that poisoning attacks can be more powerful in general. For example, poisoning attacks in machine learning can carry out targeted errors. They can introduce backdoors. We saw in this talk that privacy actually makes our protocols more vulnerable to poisoning. So an interesting question here for us is, does it unlock new attack capabilities? The second research direction is, how do we provide provable robustness against them? In the talk, we focused on settings which had natural input redundancy, but obviously an immediate question is, what about settings where we don't have this? Maybe one approach could be doing this consistency check with statistics from clean inputs that we have access to. Another general question is, how do we design protocols that are efficient? One thing to note here is this combination of DP and crypto gives rise to unique opportunities for improving our performance. The final computation is noisy in our case. So if we leak some intermediate computations under DP, this can give us privacy boost. So one question here is, can these type of leaky computations be leveraged to give a better robustness efficiency trade-off? With this, I would like to conclude my talk. Thank you very much for listening to me today, and I would be very happy to answer any questions you may have.
All right, thank you very much. Are there any questions? I'm going to bring the microphone up to you.
Yeah, thanks for the cool talk. I have a question about the input poisoning setup. So we preserve privacy for changing like one edge, right?
Yes.
But the malicious user can change all the edges that they want.
Yes.
So does that we like don't preserve privacy for malicious users?
Yes, yeah.
But that can't cause any extra leakage around, like if I was swapped out for a malicious user or something like that, or the malicious user looks at the other data to the other people and leaks extra information about non-malicious people.
Could you repeat your question?
So like if could an observer determine if I was swapped out for a malicious user?
What do you mean by swapped out for a malicious user? As in this setting, we are not necessarily swapping anybody out. It's like every edge is shared by two people. So let's say if the edge is shared by two clients, if both of them are malicious, then we can't really do anything. But the idea here is, if one of them is honest, then we would be able to catch by this inconsistency check. So we are not really swapping anybody out here.
Okay, yeah.
Okay.
Any other questions? This is a microphone. If you speak into the top. So the idea with this microphone is you're supposed to be able to throw it into the audience, right? So we'll give it a try. If it doesn't work, I've got the regular one right here.
Nice talk. Okay, this is Pan Zhang. I'm from Meta. I'm a research scientist. So like, I have a question about like the first part of the talk. So I think you are focusing on like the database setting, right? So have you ever thought about like distributional setting? So in other words, like you consider some like like ADOS graph. For example, like everyone shares like the same probability of like every edge has the same probability of P to be 1 or like 0. So the reason I'm asking this is that I believe in that case, you will get more information about the graph, right? So you will know, for example, every part of like the graph should be like the homogeneous, and you can use that information to further like reduce the impact of the.
Yes, yes. So one of the things about the guarantees that we made is we wanted them to be completely attack agnostic, and we did not want to make any assumptions of the data distribution. But you're absolutely correct. If the verifier, the server, has some extra knowledge, then we would be able to do some stronger defenses. But here we wanted to keep everything general, but with extra knowledge, we would be able to do better.
Any other questions? Couple over there. Should I throw it? All right, nice catch.
Thanks, Doc. So my question was more about the practicability of the copier. I want to understand like what this copier means in real life, like, and why does like a copier get to see my private data, copies the data? I'm trying to understand like how this copier means. Like,
Yes, so here the so think of the both of the real world example settings that I gave. So by definition of the setting, both of them have access to the copy. We are not sharing the information. For example, for a graph, let's say it's a social media graph. It's a Twitter. If I follow you, then there's an edge between us and both of us share this information. So this is by design of the problem. Nobody's explicitly sharing this information.
right. So, but you said like there exists, like you want to, there's a copier who has.
Yes, so both here I wanted to talk about settings where by definition of the problem, we naturally have a copier. Like we naturally have two parties who have access to the same information. Nobody is explicitly sharing the information.
And why does the copy not have, let's say, a malicious data? Like if I have, so I have changed something of my private information.
Yes.
Why does the copied information correct and not?
Yeah, exactly. So here, again, think about the graph, right? The graph case, like there's an edge. So both of us have copy of this bit.
Right.
Now, if both of us are allowed to be malicious, if that's the case, then we won't be able to catch a cheater because both of us will be consistency line.
Right.
But if one of them is honest, one of us is honest, then we would be able to catch a cheater.
Oh, I see what you mean. Okay. Gotcha. Thanks.
And it kind of depends on the problem setting, like whether the who has the incentive of lying. For example, in the second example that I talked about, which is the advertisement case where the client was the copier was the advertiser. So here the advertiser wants to get true estimates. So the advertiser doesn't really have the incentive to lie, but the clients here can lie about their data. So we are trying to catch the malicious clients. Yeah.
Yeah, I was wondering if you could speak to how, in your example, you can measure tampering.
Measure.
Tampering.
Oh, okay. In my.
Yeah, and early on in the talk,
Yes.
you talked about bound on the amount of tampering that could happen.
Yes. So, let's see, back to the slide. I think this should be it. Yeah.
I think the
Okay.
screen sharing stopped.
Oh. Oh. Why did the sharing stop? Okay. Give me a minute. Okay, yes. So the tampering here is literally just the error, the L1 error in the degree.
Thanks.
Okay. I think we have time for one last question if there is one. Okay. Thank you very much. Let's thank our speaker.